Hi folks, we are on the Unit 3 Day 4 lesson, and this is the second video in that. We're picking back up with example number 3, and we're going to find the scalar or the Cartesian equation of the plane that contains these two lines. So this question, I have the first line has a position of 2, 3, 1 and a direction vector of 1, negative 1, 1. And the second line has a position of 3, 0, 7 and a direction of 4, negative 4, 4. This goes back to something that I mentioned in the day 3 lesson where I said you might be given two lines and I don't say that they're parallel, but you have to recognize that. So here, for instance, you have the lines are parallel. If we called this A and B in our direction vectors, 4 times vector A equals vector B. So we have this scalar multiple of the two direction vectors. I can't just simply use both of those as the new direction vectors of the plane. So I actually have to find a different direction vector, let's say from this point to this point, and use that to find the equation of the plane. So for my plane, I'm going to have the resultant equals one of these points, it doesn't matter, one position, either one of those, plus S times one of these direction vectors, again it doesn't matter, plus T, and now I need a second direction vector, but it has to come from these 2 points. I can't just use that because that is a scalar multiple of the other one that I already have. So I'm going to say, if that say was point AB, I'll find this direction vector. So 3 minus 2 is 1, 0 minus 3 is negative 3, and 7 minus 1 is 6. So this is my other direction vector. You could have subtracted those in the other order, and that's fine too. And S and T are any real numbers. So now, to find the scalar equation of this plane, we need to do the cross product of the two direction vectors. So to find the normal, it would be the cross product of my two direction vectors here and here. So again, writing those out, negative 3 and 6, 1, negative 3 and 6, and then multiplying down and up and subtracting. So there I get negative 6 minus negative 3, so plus 3, which gives me negative 3. 1 minus 6 is negative 5. And negative 3 minus negative 1, like plus 1, is negative 2. So that's my normal. Negative 3, negative 5, negative 2. So my Cartesian equation, we start out with ax plus by plus cz plus d equals 0. And I know that my normal, the components of the normal, are the a, b, and c. So I have negative 3x minus 5y minus 2z plus d equals 0. And then I need to choose one point. You can choose either point because you know that those are both on this plane. Typically, you would choose the one point that you had already in your vector equation. So I'm just going to choose 2, 3, 1 as my x, y, and z. And then negative 6 minus 15 minus 2 plus d equals 0. And let's see, that's negative 21, negative 23. When I bring it over, d is going to be positive 23. So then filling in the final equation, negative 3x minus 5y minus 2z plus 23 equals 0. But remember, we have to put this into standard form, which means getting rid of the negative as our leading coefficient. multiply everything by -1 to change the signs. And if you had any kind of constant term that you could divide out, for instance, if you had gotten like 6x plus 10y plus 4z minus 46, you divide them all by 2 and just get that into lowest terms. So that's how to find the scalar or Cartesian equation for any plane. One thing we can do really easily from the Cartesian equations is talk about what planes are going to look like, where they're going to be compared to each other. It's very easy to compare different planes. Say, are these parallel? Are they the same plane? Are these planes perpendicular? What angle do the planes meet at? Because we do have our two normal vectors that tell us the direction of these planes. Well, it tells us the perpendicular direction, but that gives us a lot of information, really. So this is 3, 6, 9, and N2 is 1, 2, 3. So let's look at this first. We can see that N1, the normal to the first plane, and N2 are obviously scalar multiples of each other. So since N1 equals 3, N2, they are parallel. So parallel, I think, is obviously, people understand what that means. Coincident means the exact same plane. So coincident means like two planes that are exactly the same, or neither. That's going to be planes that cross each other, and we are going to look at intersection of planes towards the end of this unit. Okay. Now we would have to kind of look at, well, what happens here? These equations are unique. So this is 3 times, this is 3 times, this is 3 times, but 11 to -4, that's not 3 times, right? It's like not even connected. So both of these are written in proper form. And we can say that since D1 is not equal to D2, or I guess like 3D2, they are not coincident. So it is possible if two planes were coincident and just maybe not written in that standard form. So for instance, I'm just going to give you a plane that is coincident. If you said, for instance, x plus 2y plus 3z plus 4 equals 0, and 5x plus 10y plus 15z plus 20 equals 0. Hopefully you guys can see why this would be coincident and the other one would not, because this whole equation is exactly the same relationship, just multiplied by 5. If the d values are not in that same proportion, then those would be parallel planes because they have collinear normals. If both of the normal vectors are perpendicular to both, then those planes are going in the same direction, but they don't have the same d value. So they're just parallel, kind of one above the other. Last thing is just kind of a summary of all of these different types of equations, and some so we've got lines in R2, lines in R3, and planes. So we talked a little bit about this. First of all, why is there no scalar or Cartesian equation of a line in R3? And that's the thing that I did in the previous video where I was kind of like waving markers under the camera. I don't know how helpful it would be. It's because there's no one specific normal. In R2, if you say what's perpendicular, it's this one, or it's the scalar multiple of it in the other direction. If this line was stuck in R2. In R3, it might be here in perpendicular, but it could also be there in perpendicular or there. So there's actually an infinite number of perpendicular vectors once you add that third dimension. So we can't have a Cartesian equation using that normal because the normal doesn't exist. The other thing is, why aren't there symmetric equations of a plane? And that's because when we looked at the vector and parametric, and particularly the parametric equations of the plane, they'll have two parameters. There was an s and a t, so we couldn't solve for one of those and isolate it. So that was discussed a little bit in the video for day 3, I believe. So this just kind of is a summary, and sometimes people sort of lose track, I think, of which things that they are able to find. So lines in R2, they can have a vector equation. Yes, they do. They can have parametric equations. They don't have a symmetric equation. Remember, the symmetric equation is where you would isolate the t values and like write them all equal. If you do that, you just actually get to the Cartesian equation because we just cross multiply and solve. Okay. When we went to lines in R3, they still had vector, they still had parametric. They did not have the Cartesian. We talked about that because there's no normal, but this one was where we could have those symmetric equations. And it's kind of interesting because looking at planes, they do absolutely have vector, they do have parametric, they don't have the symmetric equation because we had too many parameters to solve for, but they could have a Cartesian equation because having those two direction vectors allowed us to find the normal with the cross product. So in some ways, you'll see the work for planes is actually more similar to the work for lines in R2, even though they are three-dimensional, or they are defined in three-dimensional space in R3, just like the lines in R3, they actually work a little bit different. And you'll see that as we move into intersections and distances as well between different objects in R3. So that is the end of our finding equations. There is a good handout on the review day for all of these different types, and basically it gives you a bunch of information and asks you to find the other equations here, or to tell different things about the equation that you're given. And it's all mixed up, which I think is actually a good idea, because it's important to be able to identify, are you dealing with a line in R2, a line in R3, or a plane? Given an equation, you should know what that equation is representing. So that is in your day 5 homework for that review, mid-chapter review day.